So, hi, I'm Rick Busarow, and you're here to hear me talk about coroutines and flow and 1.3 and all those things. So, before we get started, I saw Chris Baines do this once, and I loved it. So I'm going to post my slides at the beginning of the talk. Most of my slides will also have my Twitter handle on it. I just tweeted my slides there as well, so in case you miss it, lots of pictures getting taken. That's cool. Okay. Moving on. Again, you can check my Twitter to see it. So the most important thing by far about coroutines, the thing that makes coroutines. All right, I will. The thing that makes coroutines is the ability to suspend. And I've been using coroutines for 2.5 years now, and it took me, I guess, 2 years to figure out that icon in the gutter is actually related to the suspend. So let me just make it super clear. You should look at your gutter icons because apparently they help, and that's what it means. So in Android, we do a lot of I/O, right? And I'm sure, except for the guys that I hear talking about KTOR, everybody uses retrofit. And so everybody's going to recognize what we've got here. This is a retrofit service that's going to be making some call to the API. This is the old way of doing it, where we have a normal function which returns a call, which is wrapping whatever it is we actually care about. And when we access this, we do it using this enqueue operator, which is then obviously going to take a call back and do all of this work asynchronously and get back to us. And this is really something that we do all the time in Android. If we have something which is extremely expensive computationally, or if we're dealing with Bluetooth, which I do all the time, or the web or the file system, we're going to use these callbacks, all of this asynchronous communication. And what's actually happening when you do that is, I'm sure that in most of our projects, we have a domain layer. And then we have this resource that we want to talk to. And in between, we're not going to do that work ourselves. We're going to use OKIO, OKHTTP, and retrofit or KTOR. And high level, what happens here is that when we send a request to this IO library along with a callback, that library is then going to split it apart. And it's going to put that callback into a private data store of some sort for safekeeping, and it's going to send that request off to the resource. Then hopefully shortly thereafter, we're going to get a response back from whatever this resource is, which is then going to get parsed by the IO library. And the IO library is going to pull that data, that callback back out of its store, then invoke the callback along with the data from the response in order to continue operations back in the data layer, domain layer, sorry. So this is what we used to do. This is what we used to look at. And nowadays, since retrofit 2.6.0, which was last summer, we have the ability to add suspend modifiers to our retrofit services. So now we've lost the call wrapper around the response, and we've gained this suspend modifier. And well, this is going to cause problems. We've got that minor problems. We've got that gutter icon back, which tells everybody, and we know now that this is a suspend call that we're making. And we've got this red squiggly line because you can't call a suspend function unless you are currently inside a coroutine, which means you need to do a launch or you need to have a suspend modifier of your own. So what we're going to do here is just add a suspend modifier to this function, and we can let someone else worry about actually creating the coroutine. So now I want to introduce you to Harold. In stand-up today, Harold's boss said, "Hey, how's that bug going? Are you just about done? QA is waiting for a new build." And Harold said, "Yeah, absolutely. I'll get it to you today." Harold lied. So he doesn't know what's causing this bug. He thinks it might actually be a third-party library, and he's going to wind up, starring that repo and watching everything they do for the next couple of weeks. And he has no idea what it's going to take to actually fix this. But you are also in this stand-up, and you have some PBI that you would like to work on, which needs Harold's work to be done first. And since you don't know that Harold's a liar, you could be doing something else, but you expect him to be done soon. And his thing is, the thing that you would do with him is more important. So do you want to have that context switch, get halfway through some other task and then stop and drop everything and go back and work on Harold's thing? And no, of course not. So you're going to go get a cup of coffee and browse Twitter, and then eventually you're going to work on the thing that Harold needs to help you with. And that's a really inefficient way of working. If Harold had just told the truth and said, you know what, I think this is going to take a long time, then you would have been able to finish your other task and everything would have been more efficient. And that's what Kotlin gives us. This suspend modifier is actually a marker for the compiler which says, hey, I need to turn this into a callback. This is going to take a long time. So we've all seen this if we're using coroutines at all. You see it in stack traces all the time. Continuation impl, resume suspend crashed on, something. This continuation interface is essentially the callback for coroutines. The way it works is, well, I'm not going to show you bytecode. I can't read the bytecode, but I'm going to turn it back into Kotlin. So we strip away the suspend modifier and we take away the return type, just make it return unit, and then we add this new parameter to the function. So this formerly suspend function is actually taking a continuation where the type is this list of data which it was returning before. And that's not so bad, but that's being called by another suspend function. So do something slow is now going to get its own callback interface parameter argument. And since it was returning unit before, it's still returning unit, but now it has a continuation of type unit. And then it has to actually initialize the callback, which is going into get all data. So we have, we're passing in the required context. And note that the context that we're giving to this continuation is actually coming from the continuation parameter of the do something slow function. This is super important in this is how structured concurrency really works. The suspending functions are operating with the coroutine context of the coroutine which initially called all of them. So this coroutine context needs to be passed down as far as the suspend functions go. So we're continuing that by passing it down into get all data. And then in the resume with for the get all data callback, we're simply going to invoke our own continuation resume with unit. And that will inform whichever function is calling this one that our work has completed asynchronously without blocking threads. So this is callback hell. This is what we all wanted to get away from. It's actually still happening just in the background. And speaking of hot things, now let's talk about channels. So channels are a really good solution for handling shared mutable state. When you have multiple threads, multiple workers, coroutines, operating on the same mutable data, you can have issues where these non-atomic operations wind up doing simultaneous reads and writes and screwing your data all up. And we have other ways of doing this. We can deal with it using thread confinement, putting everything on the main thread like the UI does and like live data does. We can use atomic wrappers or mutexes, or we can use a channel, which is conceptually the same thing as a blocking queue, except that we're not blocking, we're suspending, but it's the same thing. So you have these two coroutines that want to talk to each other. They have data that they need to share, and we just insert this channel right in between them. And the interface is more complicated than this, but like for instance, the channel interface has a companion object with a bunch of stuff in it, but a bunch of constants rather. But functionally, what we're doing with the channel is just implementing these two other interfaces, the send channel and the receive channel. So this send channel is able to send using a suspend, and that's the suspending queue showing itself. If you are attempting to send data into a channel and the channel is not ready for it yet, then you're able to simply wait until it is and then pass it. If you want to be a little bit risky, you can instead use offer. You can do this from outside a coroutine, and it will attempt to immediately insert that data into this channel. But if the channel is full or closed for send, or not or, just those two, then you'll get a false back, and the data will effectively be lost. On the other hand, we've got this receive channel, which is a mirror of that. The receive function itself will wait until some data is available for consumption in the channel, and poll will ask immediately, and if there isn't something available at that exact moment, you get the null. Then, super important, we also have this iterator. The iterator is an iterator which will continuously call receive on this channel, basically allowing you to have that asynchronous stream of events piped into your receiving coroutine whenever they are available. So let's look at how this works. When we have let's just create a vanilla channel of integers and start sending to it by using a regular repeat 3 for loop and sending each value into the channel. Now, if we want to receive this, remember that we need to have two different coroutines. So we need to launch. And in order to do that, we're going to use coroutine scope. Now this lowercase c coroutine scope builder is actually a suspend function which will not return until every coroutine which was created in its scope has completed. So this will allow us to continue running this main function until we're done, instead of executing and closing out immediately because everything is happening on a different thread. So finally, it's super important that we call channel.close when we're done sending. Otherwise, since this iterator is going to be working infinitely, it's going to read those 3 values and then just suspend forever, waiting for another value because nothing has told it to stop. The cancel actually sends an exception through the channel, which is caught by that iterator, telling it, okay, you're done, you can exit your suspending function. So if we were to run this, as you would expect, we just see, sent 0, received 0, 1, 1, 2, 2. It's a nice, fair, sequential, predictable sequence. And that is because channels have something called back pressure. Excuse me. So back pressure in channels comes in 4 different flavors. We're going to talk about rendezvous first. With a rendezvous channel, you are not able to send any value until some other channel, some other coroutine is capable of receiving it at that time. So when we're using a rendezvous channel, as soon as the function begins, that receiver coroutine is going to immediately start suspending, waiting for some value. As the sender then begins to iterate and it gets that value of 1, it knows that it's ready to send that over the channel. And when it puts it in the channel, coroutine B is able to pull it back out and everything's nice and fast. Then the sender is going to get another value. And as soon as the coroutine B is finished with processing its value, it's going to start suspending again. And once we reach this state where the coroutine B is suspending and coroutine A is suspending, waiting for each other, they rendezvous and they send the data across. So it's super predictable. very, very nice and fine so long as it works. The next variety is this unlimited channel, which is in the code, it's called a linked list channel, and it's pretty much exactly what it sounds like. It has a buffer, which will just fill up with data as quickly as the sending coroutine is able to send it. The only limit is the amount of memory on the phone. So, oh good, those animations don't show up for me. So as it's sending, even though the receiving coroutine is not doing anything, the sender coroutine is not suspending. It's not blocked from doing any other tasks. So next up is the array, which is basically a balance between the two. You're able to specify a buffer size. So if you send some property and it is not received right away, you're able to send more, but at some point you will suspend until the receiving coroutine is ready to pull something out. And then finally, this is the one that you're actually going to use the most in coroutines. We have the conflated channel. With conflated channels, there is no buffer, there is no rendezvous, there is nothing. You can write data as quickly as you'd like, and if no one is listening, then they just miss out. So, last year, it was October 4th or 5th or so, first week of October at KotlinConf 2018, Chris Baines gave a really, really nice presentation on called Android Suspenders. He gave it a few other times as well, but this is the one we're going to focus on right now. It was immediately after structured concurrency came out, and he spent quite a lot of time explaining, okay, guys, your code's, you're fine. Just implement coroutine scope and everything's going to be good. But then at the very end, he gave a practical example of how to observe location updates with a channel. So we're going to look into that now. That timestamp in the corner is where this code exists in the video. I just transcribed it. So we're going to start out by this channel. This function returns a receive channel, which is, again, it's similar to having a live data and a mutable live data, where you want to expose only this immutable type for consumers. But the function itself is going to need something to write to, so we're going to create a normal channel. Now, the meat of this function isn't actually doing anything with coroutines. It's just dealing with the fused API, except for this line right here. Every time you get a location update, you're going to use send blocking, which is a wrapper around first trying to use that offer operator and then using send if the offer fails, using a run blocking. So it's basically like a fast path for what we were talking about. So you're going to use send blocking to send the location updates into the channel. And since the channel is capable of handling all those concurrency concerns, if the location updates come faster than the receiver is actually able to process them, it will be handled here. Then finally, and most importantly, aside from returning the channel, I suppose, we add a callback to this channel, which says whenever you've closed this channel and clearly nobody cares anymore about these location updates, cancel them. Really important when you're talking about something as expensive as location updates. So the problem, one of the problems with this implementation is that a channel is a one-to-one relationship. You can have one sender and one receiver. Once you've pulled the property out of the channel, it's gone. No one else can read it. And that's why we also have something called a broadcast channel. So broadcast channels are not actually channels, even though they implement the interfaces. They're kind of a different construct, and JetBrains is considering actually rewriting them to implement the flow interface. But a broadcast channel, which is really like a channel manager, is able to supply as many receive channels as you would like using this open subscription function. However, the managing of the queue of the buffer is handled on the broadcast channel side, and that's going to be really important right now. So let's take this original function for demoing the one channel and change it so that we're now creating a broadcast channel with a capacity of 1. We don't have the option to use a rendezvous channel, so I'm going to use the smallest thing I can so that I can animate it without too much work. Then we're going to create 2 receive channels out of this broadcast channel and launch 2 coroutines to observe these channels from their own coroutines. I'm going to point out that right here, that's not right. We're not going to continue iterating over this B channel. We're only going to ask for 1 value, and then this coroutine is going to finish. Whereas the other receiver is the same as before. And then we're going to send these values to the broadcast channel instead of the other channels which we created. So as soon as we start, same as before, the receiver channels are immediately going to suspend. The sender is going to get a value, and that value goes into the broadcast channel, which then duplicates the value and sends it to both of the receive channels. That makes the receiving coroutines stop suspending, and they can receive those values. Now, a couple of things are going to happen concurrently. The coroutine C is now ready to receive another value, but coroutine B is done. So it's going to kill itself off and disappear. Note that channel B is still there. So now coroutine A is going to get another value, and it's going to send it into the broadcast channel, which is then going to duplicate it, and coroutine C is going to get that value. But what happens to coroutine, the B channel? It just sits there. So now coroutine C is suspending, waiting for another value, and coroutine A is going to get another value, but it can't send it because the broadcast channel is going to say, whoa, hold on, my buffer is full. I've still got to send this 1 to somebody on channel B. So we've now created a deadlock because somebody forgot to close a channel, or maybe there was an exception, or a workflow changed, and this leaking channel is now going to create probably a difficult to reproduce bug within our code. So I mentioned earlier that conflated broadcast channel is the nice one. And that's because conflated broadcast channel is pretty much the same as immutable live data. They both have the ability to retrieve the current property instead of using an iterator just by calling .value. They're both capable of emitting the value losslessly, without loss, via send blocking, or offer, or set value on the mutable live data side. The conflated broadcast channel will never lose data sending it to this channel, but the mutable live data could if you wanted. They both broadcast to multiple subscribers, and neither one of them has any back pressure. So if you're looking for a way to get out of the live data world and into the coroutine world more, the conflated broadcast channel is going to be a breath of fresh air. It's a very easy transition to make as a mental model. So, structured concurrency. It's been a year now. Isn't that supposed to be what fixes this like leaking coroutine-ish thing, and shouldn't that make everything perfect? Well, coroutines, yes. Every coroutine has a job associated with it, or every coroutine is a job. And so when you create a coroutine from a coroutine scope, the job which is created from that launch or async is associated with the job in that coroutine scope. And then if those coroutines go on to make their own launches or their own asyncs, then those coroutines are children of those jobs. So you have this nice hierarchy where everything is linked to everything else, and you're not going to have any real leaks. So then if you decide that you need to cancel something because of a lifecycle event, configuration change, whatever it may be, everything is automatically killed and your work does not leak. But channels are not coroutines. channels are suspending things which coroutines can use to communicate with one another, but their life cycle is not part of a job, so they're a very risky method of communicating at an API layer as a behavior of an interface. Which is why a month after KotlinConf, Chris went back on stage and did another version of Android Suspenders, this time with Adam Powell at ADS. And here in their demonstration, instead of using a channel to report all of these updates, they made a suspend function. So this suspend function takes a lambda, which is another word for a callback, and which is it's not your enemy. They're okay. They help you. And so now we use the same coroutine scope builder that we had before, which means that this function is not going to return until everything inside it has completed. But then we create this completable deferred, and we never actually complete it. And you can see down at the bottom, we're calling done.await, which means that this function is not going to complete until this completable, which is never completed, has been completed, which means it's going to run forever. Except we have structured concurrency. So if the coroutine scope is canceled, if the job associated with calling this function is canceled, then it won't leak and it will go away. So then in the middle, we're doing something a little different. It's pretty dense, but we've got this job which is nullable, and every time we have a location update, we check to see if that job is null, and if it isn't, we're going to cancel it. And then we set that job to be a new job wherein we invoke that lambda with the location update. There's also a mutex in there just so that we don't have any race conditions. So it is dense, but what we're effectively doing here is creating a conflated callback, which is suspending. Anytime there's an update, any previous update that was still being acted upon is canceled, and you only have the newest data. And then this function is going to live on until the coroutine scope is canceled. So we've created something very similar to what we're going to talk about next. I forgot about this slide. So then after we're done awaiting for this thing that is never going to complete until the coroutine scope is canceled, after that, they're in a finally block, they're removing location updates. So that completes the cycle and cleans everything up. Now, if we look at just this function signature again, it's really inspiring for anybody who is up to date with coroutines, because they're doing something very familiar, and they're doing something 5 months before Roman wrote about it on Medium. If this function is obviously very, very specific to this use case, but if we assume that there's some other way to pass this location request into whatever class is doing this, then we can generify this to just be a suspend function, which takes a listener of type T. This still isn't very good because it's clearly a member function. It would need to be written in whatever class you want to operate in, but you can fix that by making some listenable interface and making it an extension function upon that. But now we don't have coroutine support for this callback. Even though we know that we're going to be doing this with coroutines, and in a suspend function, that lambda is not a suspend lambda, so we can't delay or anything like that. But what we could do is simply mark it with a suspend function. Or, since the larger function is guaranteed to be in a coroutine, since it is a suspend function, what we can do instead is to make the function an inline one. Now, if you were to do this without removing the suspend modifier on that callback, you would actually get a warning from the IDE telling you that the suspend modifier on the lambda is redundant, because now that code is not going to be executing in this function. It's going to be pulled out and put into the calling function's body by the compiler. So it's guaranteed to be a suspending function. And what this means is that we can now write code like this, where if we have a listenable which we want to observe, instead of writing a 45-line long function with a bunch of parameters and a completable deferred, which is never completed, we can just use this single function with a single parameter and a lambda, and it's so much cleaner. And they weren't the only people to have this idea, because now we have flows. That's pretty much what a flow is. So a flow is stable now, kind of, as of Kotlin 1.3.0, which was in August. There are still quite a few operators which are marked as flow preview or experimental coroutines API, but all of those are operators that are dealing with channels, because no one is happy with how channels are right now, and so we're not going to stabilize anything. So you've heard, I'm sure, about cold streams and hot streams and cold flow, and if you are already familiar with reactive programming, then that's great, and that's probably all the explanation you need. But since I wasn't, it didn't make a lot of sense to me. So let's say you have a property in some class, and it's going to be initialized as soon as that class is initialized. This would be considered eager, but if it was a stream, it would be considered hot. As soon as the class is initialized, all the work starts. If find last name wasn't just returning a hard-coded RIDA, if it was doing something more expensive, that would be a problem, and that's why hot is not considered to be all that great. So we have a compromise. We have something called a lazy, which in Kotlin is, of course, the delegate. In this case, it would be evaluated once the first time it is accessed, and then never again. This memoization is sometimes really great for optimization. Other times it's not all that necessary. But we do have another way of doing it. This find last name function is effectively cold. It is not evaluated until somebody calls it. Similarly, we could express that as a lambda, where if you wanted to access first name, you would access the lambda and then call .invoke, right? So this looks really weird to do as individual properties, but this is what we do with reactive streams such as flow. So you can create a flow in basically two simple ways. The first is the same as if you're declaring a collection, like a list or an array, just flow of, array of, list of, same thing. Or you can define a lambda. There's a lot more code which goes on behind the scenes, but in this lambda of repeat 3 emit it, that will not be evaluated until the flow is accessed. And then every time that flow is accessed, it is going to be evaluated again, the same as the first name lambda in the previous example. So on the other hand, you have to collect these flows. You can't just call .invoke. And you do this again with a lambda, where this lambda is invoked every time there is an update to the stream instead of once for the entire stream. And these are called the flow builder and the flow collector. So if we were to run this function, we're going to see starting only printed one time, then we're going to collect everything and then finish. Pretty simple. If we were to have two collectors, unlike the channel where the second collector would not have any data, if we run this, we're going to see that the same exact sequence is executed every single time. That means that the flow is not stateful, it's just a sequence. It's a really concise way of expressing a sequence. And since it's a sequence, they don't inherit from sequence or implement sequence, but they have the same operators. So for instance, you can filter on a flow and you can say, only give me the values which are even. And if we were to run this, yep, you get 0 and 2. Or you can elect to only take a subset of the flow. You can say, for instance, take 2. And this is interesting because if you say take 2, on a flow, it doesn't execute the entire flow and only give you the first ones. It will stop when it's done the work that it is actually asked to do. So the flow is very, very conservative in its work. So let's say we have two different flows, which are defined very simply because I need the space. You can also make a flow of flows by converting them to a list and then converting that list to a flow. And the reason you'd want to do that is so that you can use operators, intermediate operators like flatten merge. Flatten merge is your best friend if you're using flows with MVI. It's capable of observing all flows concurrently and then updating the output flow with whatever value is emitted as quickly as it is emitted. So in our case, we're going to take this and we're going to add a when block to the collect and say if it's a string, print that it's a string. If it's an int, print that it's an int. And if we run it, we'll see this output will change slightly with each time, but we're able to differentiate between what those values are, but we do get everything. So if you have intents, which you need to filter on, if you want to have a single observable flow in a view model, presenter, interactor, whatever it may be, you have a sealed class and you have a nice when block with all of your different intents. And the difference between doing this versus just observing everything individually is that this is an atomic operation. If you have two different intents coming in, which would update your view state in similar ways, and they're going to be accessing some block of code to update your view state at the same time, then your behavior can be really irregular and difficult to debug. So when you have a flatten merge, then everything is happening one at a time, and your updates will any new update to a flow will not actually be executed until the previous ones have. So you don't lose any state at all. So speaking of Android things, let's talk about actual practical coroutines instead of just print statements. When we finally updated some of our code to use Flow, I got a lot of questions right away about how do I actually send things to a flow, right? We've seen the flow builder, and that makes sense, but if you're from the channel world like my team was, or if you're in the live data world, then where's your post value or your send or your send blocking? So if you try to do a .emit on a flow from outside, you've seen it working in these lambdas, but you can't access it because that's actually a function on something internal to Flow. What you need to do instead is to use our old friend, the conflated broadcast channel. Your conflated broadcast channel is, you can convert that to a flow simply with as flow, but it's also stateful. And it's a good concurrency primitive to make sure that you have these atomic operations. When you just use straight flows, you don't retain any state. If you have some value from a database, for instance, which you're updating, and then you undergo a configuration change, like rotating your screen, do you really want your flow to have to pull all of that data again from the database before it shows up on your screen while you're spending a second showing some default state when the user already knows what that data is supposed to be? No, of course not. So that's why you have a conflated broadcast channel in between your data layer and what you're actually going to be showing on the screen. And this allows you to make, if you're not ready to go full MVI, UDF, all that stuff, you can use a broadcast channel and emit to it internally, just like you would with live data. So I'm going to take a stab at location tracking as well. In their versions, remember that the channel had to be closed in the first version, otherwise you would leak. And in both versions, you had these solutions which only work for a single subscriber. The channel can only be consumed by one, and the suspend function would need to be invoked by different coroutines in order to get that data, which would then mean that you're requesting location updates from multiple sources, which, by the way, in the Fused API would mean that the first one was canceled. So what we're going to do is have a location service, and I'm just going to have Dagger provide the location client so I don't have to think about it. And then instead of exposing a broadcast channel or a suspend function, we're actually going to have a flow as a property. Now in this flow, which is, by the way, a broadcast flow, this is not actually part of the Coroutines library. It's something which I wrote in a gist, and you can see that the link to that up in the corner. In a broadcast flow, we're going to do essentially the same thing as Chris. We're going to use ascend blocking to update a channel with every single location update. And then instead of using invoke on close, which is a channel operator, we're going to use await close, which is also a channel operator, but with a different name. It does the exact same thing. So with a broadcast flow, the flow is actually aware of how many subscribers it has and will start automatically as soon as someone observes it, but then will stop automatically as soon as the last observer leaves. So this is not something which can be achieved with either of the other versions, and so you should use it. And last thought, if you guys watched the ADS streams or went back and watched the videos later for this year, you saw this. Jose and Yeet on stage telling everyone you may not need live data. So as of Lifecycle 2.2, which is currently in RC2, so we are going to see it very soon, we have something new called the Lifecycle Scope. And that Lifecycle Scope also has extension functions for launch when resumed, launch when created, and launch when started. So if you use those, if you're using, say, launch when resumed, and your screen pauses, all execution with your coroutine automatically stops. It's not exactly the same thing as live data. There is some subtlety there, but we're reaching a point where we can really use coroutines for single shot requests, for lifecycle aware activities, have them automatically stop, have them automatically resume again, and have a single unified UI from the data layer all the way up to the UI using the same library instead of trying to bridge things between live data and coroutines. So that's all for my talk. Here's the slides again. The JetBrains documentation is very, very good for asynchronous flow. Links to the different YouTube videos. My name again is Rick Busarow. There's my Twitter, my Medium, and my Kotlin Lang Slack. Thank you so much for your time, and I hope you have a nice rest of the conference.